Okay, welcome back. And this is really it. Friday we'll meet and we'll be together, but that's really it. Friday will be really prepped for the exam, so I'll have a little bit of a different flavor to it. We're really just finishing up that final exam topic, the final cache topic, and just understanding a little bit more about the performance of caches. I think it's an important topic to cover, given how late we are in the semester and our exam is on Saturday. It's not going to be none of these questions will be on the exam, but I still think it's important to understand caches. So we kind of understand caches somewhat in isolation as these kind of still somewhat abstract components, and I just want to discuss with you what this means in terms of real systems, both in terms of organization of cache as a hierarchy in real systems, as well as what that really means from a performance perspective, how we can take the cache access patterns and hit and miss rates and calculate the impact on performance. But this is for our own just personal edification for us to really learn more and be more complete engineers, and we don't need to really worry about cramming for this for any upcoming exam on Saturday. So uh, where we left off um, on Monday is this is just a die photo of relatively dated but still real world modern CPU that shows that the cache is obviously critical just from a real estate perspective in terms of where our transistor budget is being spent, and a lot of it is being spent on cache. And the next thing you may notice is that there's several different boxes listed as being cache here, and we actually haven't talked about that. We've talked about how cache is relevant in the context of both instruction accesses as well as data accesses, but we haven't really talked about it um, in terms of what does that mean from an organizational perspective. So a couple questions. I'm seeing some exam questions in there. So we are scheduled from 7:30 to 9:30 on Saturday, and you have that entire time on Saturday. I have scoped the exam to be of similar length. There we go. We got it. So that is the policy as stated in the chat there. So it's scoped to be of the same length, same amount of points as the previous exams. I'm not going to cut you short after 50 minutes and say, well, you've had enough time. You have the entire time to work on it. I don't think you'll need the entire time, but you'll have the entire time. Got it. Okay, so we talked about instruction versus data memory accesses, but you can actually also see here, that's the first thing you may notice, is that when looking at a quote unquote real cache, certainly the photograph of a real cache, you can see that it's actually separated out. So you have it's referred to as fetch, scan, align microcode, your instruction fetch part of your pipeline. Um, and then you have a separate cache dedicated to that access itself. Likewise, you have your load store units that are determining what the addresses should be for my load and store instructions and type of instruction. And you're going to have a separate cache associated with that as well. So we've already been doing this, right, to avoid structural hazards in our pipeline. And just because it makes our processor a lot easier for us to implement and separate, um, we have physically separate interfaces already. So that's gonna extend to our cache concept as well. That at that first level of access of the cache, you will have both instruction caches as well as data caches, and they're separate. They're physically separate. There's ultimately a shared address space between the two, but there's a physical separation in terms of how we would access those. The advantage of that is the same as it already was for our textbook implementation of the pipeline. So we've gotten rid of those structural hazards. We don't have to worry about something is doing an instruction fetch while something else is doing a memory load, and how do we interleave those operations? We don't interleave them at all. It's two physically separate memory. Um, so that would be a problem if we just had a single ported kind of singular cache that we have here. There's definitely a disadvantage. There's some disadvantage of having that partitioning of caches between instruction cache and data cache. Well, and that's because that partitioning is a very static thing that is done at design time, where you've said, I'm going to have an instruction cache of a certain size and a data cache of a certain size, and they're going to have the following characteristics. And it really depends on your application to what extent your application really stresses or makes best use of those caches. Some may have really large code segments for a very relatively small amount of data. That's what that's trying to show here. Big code, little data. Or the converse could very likely be true. Maybe that's more likely to be true where we have little code and big data. So a small amount of static instructions operating on a relatively large amount of data. Well, we've done this static decomposition then into instruction and data caches, And maybe you wind up having a data cache that really could have been bigger, that would have been a lot better, and an instruction cache that you're hardly using. That's kind of the downside of doing that. The working set term is not one that we've used this semester. That just refers to the amount of bytes, the amount of data that an application tends to need in the steady state. Um, and that can very much be the case that we have this static, usually mostly equal partitioning of instruction and data caches, and it depends on our application. For some, we're okay if that's the case. For others, maybe we're really not using those caches as effectively. So we have that level one cache, and I've mentioned the term, but that's what this is referring to. That first layer of cache that we're accessing from our CPU's data path. Modern microprocessors tend to have several layers of these caches, and it's referred to as a cache hierarchy, where you have this first level of cache where our goal is to have as many of our memory accesses be satisfied by that. It's relatively small and it's relatively fast. That's our trade off that we've always been exploring. Then we would be following that with a second level of cache. That's going to be a relatively larger and relatively slower cache than the first level of cache. And then that can continue. You certainly have many systems today that have level 3 cache, and there was a time where people were really exploring, well, if 2 layers of cache is good and 3 is better, why not 4, 5, 6, 7, 8, 9? You don't see that anymore, but there was certainly a period of time where people were very heavily exploring that concept. It turns out that at least through empirical study of real applications, if something's not found in your L3 cache, an L4 cache isn't going to help you either because there's just not enough locality with that particular data that's not found in the larger caches. So you have this kind of trade off, which we already saw, right? There was already a trade off between what our main memory was able to do, very large storage but very slow, and what our cache was able to do, right? Very small amount of hardware managed storage but very fast. That L2 cache, or going further, that L3 cache, is just another data point in that trade off space. Where the trade off is, let's make an even larger cache than what our L1 cache was. Nowhere near still as large as what our main memory would be able to support. It's still storing a fraction of our total address space. But it's still going to be slower. It's going to be, because it's larger. I think a hand wavy argument is sufficient that because it's larger, the signals have to travel further. We're not going to be able to access it as quickly as our even smaller cache. So a larger cache that hopefully has an even better hit rate than our L1 cache would have, but our access time for it is going to be slow. And that hierarchy is kind of one of those big ideas, important concepts of cache organization. That you focus on a small L1 cache where you just want to be as fast as you can, but because it's small, perhaps you're missing on things that a larger cache would be able to hold. And then you have successive hierarchies of cache, successive layers in the hierarchy that are larger but a little bit slower, where maybe you can focus on, because of its size, you can focus on having even a better hit rate associated with it. So that the hope is, ideally, everything gets hit in my L1 cache. If not, L2 is a cache for the L1 cache, right? Cache, as we talked about, is kind of a relative term. Register file is kind of a cache in some sense, a software managed cache for our main memory. L1 caches, then L2 can cache L1, or etc., and it goes all the way down the chain. Even our main memory is a cache for our solid state storage, which itself could be a cache for our networked storage that's even further away. So instead of just having this one static cache, we have potential multiple layers of it. So going back to that Opteron processor, that was the die photo. This is what a quote unquote real world cache, would look like, where those terms that we've been using to describe the cache are still very much the prevalent terms used today to describe caches. So they have a certain size associated with them. Usually, when a cache is described by a size, so the L1 caches are 64 kilobyte caches. That refers to primarily just the data storage in the cache. And I want to make sure that's clear, and it's clear in any quiz question like we may have today or on any exam question. When a question asks and says something about the size of a cache, it has to be clear what it's referring to. And we really have two different things that dictate the size of the cache, or it could be valid descriptors for the size of the cache. One is how much valid data does my cache store? And that's what this is showing, 64 kilobytes for that L1 instruction and data caches on the AMD Opteron. A separate and, equally important thing is how many bits of storage does that cache require? Those are both kind of sizing issues. Often, but when you usually refer to the size of a cache, we're referring to how much valid data is it storing. But we now know, as we're understanding the different trade-offs of cache architectures, whether it's two-way set associative, whether it's write through or write around, etc., we know that there's those additional bits we have to put in the cache to just keep track of things. If nothing else, our valid bit and our tag bits. But we saw some of the other things we may need: some least recently used information, some a dirty bit for the write back caches. There's other things that have to be stored in the cache for us to be able to support that 64 kilobytes of data. So I just want to make sure that that's always clear whenever I would ask you something about that, or the textbook or a homework asks you something about that, which is cache is 64 kilobytes. That's how much valid program data or instructions are being stored in the cache at most at one time. The actual physical size of the cache is a certain percent larger. And we can calculate that out because we can take our address fields, we can figure out how many bits of that are required to be the tag. And the math is still exactly the same. There's this many blocks, that's how big our index field needs to be. There's this size of each block, that's how large our block offset bits need to be. The rest have to be tagged. We can then take that information and calculate to the bit exactly how much storage a cache requires. So going back to the Opteron's cache, it's just a larger version of what we studied, what we kind of sort of understand at this point, certainly as of last Friday. Two-way set associative cache with 64 byte blocks. So that's a cache that has some flexibility, a little bit, right, with where things are placed. Not as good maybe as a four-way set associative, but we know there's that trade-off involved. And has a 64 byte blocks, which none of our pictures we've been showing have had that wide of a block, but we've discussed how spatial locality is as important as temporal locality, and you need to have those wide blocks to be able to take advantage of it. So if a single byte is requested by an instruction now, this cache line would bring in the entire uh, surrounding 64 bytes around it. So in theory, you could get a very good hit rate if you have a lot of spatial locality. With a 2-cycle access time, that would really mess up our processor where we assume everything is happening in one cycle. But 2-cycle access time is pretty good otherwise, right? With these deeper, more complicated pipelines, you can work around a 2-cycle access time for your data memory. Compare that to the L2 cache in the Opteron. Well, the first thing you can see, it's a lot bigger. So now we're looking at a cache on the order of a megabyte. And also maybe you can see that the focus is even more on trying as best we can to have as much things in the cache as possible. So just larger, and also now four-way set associative versus a two-way set associative cache. The system design philosophy behind this and many of our cache hierarchies is make L1 as fast as possible. For the higher order levels of cache, just try to get as high of a hit rate as possible. So that ideally you just never have to go to that main memory, or as infrequently as possible. Similar 64 byte blocks, that tends to make sense. We want to replace an entire block when there's a miss in that next level. You can have different multiples of that, but very often they're going to be the same block size from L1 to L2 to L3. And then the access time for it is 16 cycles. So that's a penalty, right? So 16 cycle stall would be very detrimental to our 5-stage pipeline processor. Even in this processor, it would involve some sort of stalling of the pipeline or having to reorder instructions and deal with that. But it's still way better than the access time associated with then missing entirely in the cache and going off into main memory, which is always going to be on the order of hundreds of cycles for a modern system. Here's another real design. This is a Intel Core i7. Back when that name meant something and you could actually determine what a processor was by its Intel branding, this was the initial Core i7. Microarchitecture was referred to as this is Nehalem based, or it was their Bloomfield line of processors. This is a very early Core i7. Haven't really changed all that much in terms of what you get from an Intel processor here versus what was this 6 or 7 years ago now, and it's really just more of the same. So now this is a multi-core processor for which, for better or for worse, the entirety of our course is 1/4 of this chip, right? And even less than 1/4, because there's a lot of things going on here that we don't get to cover till a more advanced till a more advanced topic architecture course. So be it. But even just looking at that one region that we um, have built our version of this semester and ignoring the rest, we can still see a big chunk of that real estate is being spent by cash. And it's not labeled at all here, but you can tend to tell via the very regular structures when looking at a dye photograph that cache is just these really large arrays of SRAM cells. So you can usually determine where the cache is, even if Intel doesn't label it for you. This would be your L1 cache. Um, some part of that. This would be L1 instruction, L1 data. Relatively, as we'll see, small L2 cache, but then made up for by having a really large L3 cache in this particular system. So whether it's one layer, two layers, or three layers, the design of the cache is still the same. It's just a different point in the trade-off space of size, configuration, hit rate, and access time associated with that cache. And so we can look at the stats for that as well. So this would be one way to kind of logically view what's happening in those caches. It's only showing the data path here, but otherwise it's still the same. And all processors effectively have that same organization where you have an L1 instruction cache and an L1 data cache. And then it's very common that at those successive layers of cache, we no longer have to worry about structural hazards anymore, right? Once we have a miss in a cache, structural hazards become a lot less relevant to us because we're already waiting for dozens of cycles potentially. So this would be a split cache still with a copy of it or a version of it for the instruction and a version of it for your data fetch paths. Then your L2 and your L3 and certainly your main memory would be a unified cache, a single cache that's satisfying both sets of requests. So the L1 is split with 32 kilobytes for that individual red box that we had highlighted there, with a different organization between the L1 instruction cache and the L1 data cache, where it just so happens the L1 is four-way set associative, the L1 instruction cache is four-way set associative, and the L1 data cache is eight-way set associative. And why? Who knows, right? Fairly well compensated engineers at Intel projected out for the applications of merit for this design of a processor that it was worth the trade-off to have more set associativity in the data cache than in the instruction cache. Ultimately the numbers kind of prove out whether that's a good design decision or not. I think even though we intuitively can start to understand how caches operate and why having set associativity is a good thing, we can always come up with synthetic examples that show having four ways better than two-way and eight-way better than four-way. Knowing precisely that that's the right design decision to make is something we can't really answer ever via some analytical model. We have to have good empirical data that tells us it's worth the trade-off to spend those additional transistors to potentially lower our access time for it, but to certainly spend additional transistors to have an eight-way set associative cache, but only for the data accesses. For the instruction accesses, it's just perhaps just not worth it. There's an L2 cache, which is unified, which is also eight-way set associative. And then you have your fairly large, I would call it L3 cache, which is actually shared across all those different cores, which is actually 16-way set associative. So this is a pretty good example of successive layers, relatively small, focusing on really fast access time, getting larger and trying to improve upon the hit rate. And then finally, L3 cache, doing all you can, spending a lot of your transistor real estate to make sure that we just don't want to go to main memory. We want to minimize our total number of accesses to our main memory. We've got 93 people here, which is pretty much our high water mark outside of exams. So let us take a minute here and let's navigate to Canvas together. So the message was generally received that today would be a quiz day. That's larger count than our previous quiz. I don't feel so bad about it. So head on over to Canvas. It'd be listed as quiz 11. And this is our very final quiz. I mean, it has to be, right? Our semester's ending here. I don't know. Email me if you want to keep going next week and the week after. It doesn't matter to me. We can just keep doing this. Get extra value for your tuition dollar. I'm perfectly fine with that. Quiz code, and someone can enter it in the chat because I know some people are just listening or can't see my screen, is KH28 is the quiz code for today. And let's take about 4 minutes on this quiz. Thank you, James. Take about 4 minutes on this quiz, and let's just do our best with it. So you can get started. Yeah. Sure. Let's just take another minute or so. Yeah, it's a good use of our time anyway. So let's take one more minute, and then we can all do this together. That is fine. Okay. I still haven't gotten used to this part. It's very awkward. I just see some people staring at me. And I'm just not sure how many people are done. If it's in class, it's much easier. You can kind of just see if people's, are moving on to other things, or I guess I can see how many people have hit submit on it. I guess I can get some data here as opposed to just sitting around guessing. All right, we did okay. Well, let's see here. People are still on that first attempt, so let's take another 30 seconds. We have a full 24 minutes to finish this quiz, so we should be okay. Just another 10 seconds. Okay. All right. So even if you're working on it, that's okay. Let's just go over this quiz, and that's fine. So, uh, it, again, and I've mentioned that quizzes are for just one way to measure class attendance and participation, and just mini checkpoints. They're not supposed to be critical in and of themselves. That was never my philosophy on them. But when I first taught a course like this, I would just walk in the class and say, let's have a quiz. And, that didn't go so well because it wasn't as predictable and students felt that they were missing out. But that's all it's for. It's just to see who's there physically, mentally, and so forth. And even if you're confused on it, that's a good thing because it's also, this is kind of our final opportunity to get a chance to look at what those Canvas type questions for a course like this tend to look like. I'll note that for better or for worse, I have this habit of going at the question. You've maybe seen this in the lab assignments and in some homeworks as well, where I try to highlight things that I think are important. But then when I don't highlight something, maybe it's considered not important. And so I look at what I've bolded or highlighted, but don't assume that that's the only important part of a question. The entire question is important. So I could bold the entire thing, but then that defeats the purpose here. We did already mention this today, and I think that's valid. Of the size of a cache, the question itself has to be very clear what it's asking in terms of sizing of the cache. And this one is clear in the sense that it says how many bits of data. So that you don't have to worry about tag overheads and things like that. That would also be a valid question. How many bits of storage does this cache have? We can answer both of those, but this one is only asking how many bits of data does the following cache hold? Now, in terms of things I didn't bold, bolding bits is probably important as well. So if you answer this in terms of bytes, on a paper exam, if you write, I don't know, I think it's 16 bytes, I give you full credit. On a Canvas auto-graded thing, you get 0 points. So that's the trade-off. That's unfortunate there. But it is asking for bits of data. So your answer would be in the form of bits. Let's walk through the steps of that. We talked about last week, even a little bit on Monday as well, that to understand a cache organization, you need to be able to see the address mapping. And that these questions almost always just come down to the address mapping and then connecting that to an organizational picture of what the cache could be doing. And this one, maybe it's easier because it's only 16 bits and so forth. But it does tell you everything you need to be able to figure out that address mapping. 16-bit address space, direct mapped. The block size is 1 byte, so that satisfies certain things. Let's walk through those in kind here. Let me open up my little whiteboard here. I didn't have that open. Okay, so that's old. That's our logical view of what's happening architecturally, and now today we did see some connection to that. But let's go back to this particular question and what that means from a cache perspective. So we know that our address field is 16 bits. So this is address. And the question could pose this in different ways, and they're equally valid. You could argue that this is a backward way of saying it, but it's actually an easier one as well. So if the block size is 1 byte, that means we don't have any block offset for this. So talking about caches that have some spatial locality, and then there's some bits potentially dedicated to offsetting that and separate mux at the end. We don't have any of that. So there's no bits dedicated to that. So this address line is going to be split, not necessarily in half as being shown here, but is going to be split between tag bits and index bits. That sucks. Okay. Yeah, there we go. Between tag bits and address and index bits. And the nice thing about the question, in a sense, it's a quiz question. The cache index is the 4 least significant bits of the address. I could have phrased this different ways. I could have said there's 16 blocks in the cache. Would have been a valid way to say the same exact thing. There's 4 bits in the cache index. Well, let's draw that out just to make sure. So this would be 4 bits. How do you want to best visualize this? This could be bits 3 down to 0. That's fine. Or you just put somewhere that this is a 4-bit value, right? That's how the textbook is showing it a lot of the times. That also tells us, without telling us, through very simple induction here, that the remainder of the address bits are the tag bits. And again, which exact bits they are doesn't matter. Much more that what matters is the actual size of that. So it's 16 bits total. If our index is 4 and there's 0 bits for the block offset in this particular cache, we got to get to 16. We always have to have the entire address. We can't decide to use some of the address. We have to use the entirety of the address. So 12 bits for that tag field. Let's go back to the description of the cache. It's direct map. So that's all then we need to know. So it's that single kind of structure where we have our blocks in the cache, and there's only one way a block can be put in that cache for a given address. There's not multiple copies of it where we have two-way set associative or four-way set associative. So if we were to draw then this cache, and whether you want to or need to physically draw it out, having a version of this in mind definitely helps. That there's 4 bits of our index field, and that would mean then there's 16 of these things. 16 blocks. And we know that that's our data. That's our actual blocks of data. So to answer this question, which is easier than it could have been, and maybe an exam version it could ask a slightly different flavor of this question, it's asking how many bits of data does the following cache hold? By telling us that there's 4 bits for the index, it's telling us there's 16 blocks in that cache. And it's not two-way set associative. If it was two-way set associative, there'd be ultimately 32 blocks in that cache, right? One for way 0 and one for way 1, right? But it's telling us it's direct map, so there's only one place to put things, and there's 4 bits to index into that cache. That means there's 16 blocks, each of which we're given here as being just a single byte wide. 16 things of 8 bits wide would give us an answer of 128. I didn't check, but I think that's correct. If the question had instead asked how many total bits of storage would be needed for this cache, we could also answer that. There's maybe a little bit more detail we'd want to ask in the question to make sure it's completely unambiguous, but we have enough to kind of get really close to that. Because we know when looking at this cache, it's not just the data that we're storing there. I mean, that's important. The data that we're storing is important there. It's also the other things in our cache. It is the tag bits. And there's going to be 16 copies of those as well. And we know exactly how wide those tag bits are also, right? We can't guess at it. We have to know it has to be the remainder of that address. So 8 bits of actual data, you could argue this is an inefficient cache in the sense that, less than half of our total SRAM storage is being spent on actual data storage, and the rest is being used to just manage a cache. It doesn't seem worth it, but that's not what the question is asking. It's asking potentially how many bits of total data storage, and we know we need other things as well. We need a valid bit. Do we need a dirty bit or not? Well, that depends. Depends on the cache organization and how it's handling writes. The question would have to tell you whether it had a single bit for dirty information or whether it was a write back cache or not, right? If it's a write through cache, our cache values are never dirty. So 8 bits, 1 byte blocks. That's just what the question said. There's no block offset. Every block is just 1 byte. We're storing 1 byte per entry here. Whether or not this one is actually needed depends on the question. There wouldn't need to be any least recently used storage or anything like that because it's direct map. We don't need to keep track of any of that extra metadata for this cache. We do need a valid bit though. So at the very least, there's 1 additional bit there. And you could argue, and it depends on what the question says, that there's an additional bit of storage there. So now each index in my cache has a block of data and has 22 total bits of storage. So if the question had asked that, how many total SRAM bits of storage do you need to implement this cache? You could also have answered that. That's also perfectly valid. That's 22 times 16, 300 and whatever, 52 or something like that. Total bits of storage, that's not even close to correct. Total bits of storage needed for this cache, but 22 per block is what you would need to answer for that particular question. Let's go on to question 2. So the answer for this one, which doesn't ask that, just asks how much bits of data does it require. That's just 128. 16 blocks, each 8 bits wide. Okay. Don't recommend doing math in your head in an impromptu way. So this question is okay, and if you said you were confused on this question, that's fine, but that's a sign you do need to kind of prep for Saturday, more than maybe you were already planning. And it's okay. You have time. It's Wednesday. You have till Saturday. Only because this question was exactly asked, about a week and a half ago in class. Right? We did this as an in-class exercise in class. So that's okay. If you look at it and say, well, I have no idea what's going on here, you're fine, but you have some work to do. So don't forget that and take that as your lesson from this, not the actual answer to the question being that important, but um, the fact that there's nothing new in these quiz questions. It's asking the same kind of stuff we've been asking, during the semester for homeworks in the end of the textbook. There's no trick questions in this class. I don't believe so. Okay, so it says for the following cache and for the cache state shown, what byte is read from the cache? Use the exact representation given. So, OX, this is the attempt to auto grade it here. Or is there a miss? And write miss. I'm pretty sure I put in capital MISS and MISS all in caps are also valid. But in general, if it's an auto graded question, and if it looks like this, it would be, and all of our quizzes have been auto graded, you want to make sure you get the exact representation of what the question is looking for. There's very, very little of that on the final exam here because it caused us more grief than it saved me time in grading. Okay, so for the addresses below and the cache state shown, so what's in the cache here matters. What byte is read from the cache, or is there a miss? And the nice thing about this question is a harder version of this question could omit this address mapping entirely. That would still be valid. You'd have to then describe the cache and say this is a direct map cache with 1 byte blocks. You'd have to do with 2 byte blocks. You'd have to do all of that and to get to the address mapping. But this question gives you the address mapping as the diagram. So here you're just kind of following the signal and figuring out for a given address, what does that mean in terms of tag, index, block offset, and trace this logic to determine whether there was a hit or not and what that data was. Let's do the first address at least. Thank you. The first address is 1010, and I think it may be counterintuitive to look at that and be like, well, I actually care most about those middle 2 bits to start with. I understand, we logically kind of want to just go from, right to left or left to right when looking at values. Given our address mapping, all these bits are necessary. They're all important. But it's actually the middle 2 that are, most important to get us started here, right? And if I was doing this, certainly on paper and pencil, I would like circle these 2 or underline those 2 and do it for all of those cases. So I have no confusion about which ones I'm looking at first. The truth is of these kind of cache questions, whereas if you do this question and you decide that this is my index, either because the question didn't tell you or you did the mental math wrong or just logically a little confused, the unfortunate truth of a cache question like this is if you do that, you're running the risk of getting a 0 on that question. It's hard to give partial credit for that kind of answer that traces the cache entirely wrong. So it is really important to say, given my address mapping, what row in the cache am I interested in, and to do that consistently throughout. So that's word of warning, or that's just the reality of those kind of questions. You go down in a completely incorrect path, and you can't really recover easily with partial credit when you look at the wrong bits of your index. So that's very important. So for this one, we're looking at the middle 2 bits of my index. We have to kind of do that binary conversion, I guess, but usually it's just a few entries, so it's not too bad. 0, 1 would be index 1 in my cache. So I know I'm looking at this row. And we know, hey, it's potentially a hit because there's valid. And it's actually a hit because my tag is matching. And not only is it a hit, we grab both of these bytes. The one we actually want would correspond to bit 0 for my block offset 0. And so the answer for this one would be 0xDE. And you can trace the rest of the way through. Figuring out the misses tends to be easier, right? If the middle 2 bits for this example are 1, 1, it's always going to be a miss. So that one, without even doing any actual logic, once you get to miss, you're done, right? 1, 1, it has an invalid entry there. There's something there, but it's not valid. Garbage in the cache there. That's going to be a miss. Likewise, another approach you can take is to work kind of backwards. I can't annotate this screen like this very easily, is to actually calculate what address is stored in the cache and just label that near the cache somewhere. because it's always that same combination of index and tag. So this is storing 000x, this first row. So it's 0000 and 0001 because of the tag. This is storing 1010 and 1011. Well, there you go. This is storing 010x. And this one's storing 111. Well, actually, it's storing nothing, right? Because it's invalid. If it was valid, it'd be storing 111x in the cache at that location. That approach may also work for you. It's kind of figuring out exactly what is in the cache address wise, and then when I give you address strings, you've already drawn it out. Depends on the question, depends on how big the cache is. Is that going to save you time and headache versus just doing it address by address? It's hard for me to say, but yes, there's equivalent operations always. Okay, so congratulations on completing your final quiz of the semester. Or if you're desperately doing it right now, that's fine. Congratulations on that. Um, I had mentioned a couple times, just mention it one final time, that I will give you quiz credit for doing the course evaluation survey. It is like a 4-question survey. They used to be like 17, 18 questions. And just fill those out and provide positive feedback for those, or critical feedback for those. I do read all those, so you have to be a little careful with what you write. Um, I don't try to do any grammatical analysis and cross-reference to assignment or exam submissions. I could, but it's not that important to do that. But it does get read, so take that into account when you fill out that information. That I do read what you write. So put some Easter eggs in there. That's fine. Okay. Final thing, and this is definitely just important topic, but we're going to get to a little bit of it, and it's there in chapter 5 for you. And the semester ends, so be it. Like many things in computer architecture, and some people find this very satisfying, and others are always trying to apply additional analytical rigor and modeling of things. And both approaches are fine, but like many aspects of computer architecture, it's a very empirical discipline. We can have models. We can behaviorally try to estimate what architectural decisions will make sense. But if you look at a computer architecture focused company, the vast majority of their engineers, of their employees working on the architecture side, not on fabrication and things of that nature, are doing performance modeling. They're running experiments, usually with simulators or with emulators, and it can be simulators on top of simulators on top of simulators. They're running those simulations to get a good feel for the design space for that next generation of chip that they're working on. So it's an empirical discipline, and that's all I mean by that. That we run experiments to figure out what the right solution is for what we want to do. And that happens in our performance questions that we have in this class. Is doing this a good thing? The answer is it depends, right? Almost always, right? And it depends on that experiment that we would need to run that gives us a good estimate for as good as our input is, our output tells us something about the performance of the underlying system. And that has been done to death. I mean, it's a very active academic area, and in industry as well. A big part of one's job responsibilities, if you have the title of computer architect, is doing performance projections and modeling. And the actual VHDL isn't that hard, at the end of the day, right? I mean, we have to learn that, we have to do that. It doesn't get that much harder than what you've done this semester. It just, the scope gets a little bit larger and wider. So we can look at that and figure out, for caches specifically, what the different trade-offs are involved in cache. So this first graph, this is straight from chapter 5 of the textbook. It's showing the data cache miss rates for 8 different cache, I think it's 8 different cache sizes here, and how it changes as the associativity increases. This gives you some part of the answer. Of course, your data is only good as your input. So for I'll say this caveat once and then we'll be done with this. For the benchmarks being benchmarked here, for the rest of the system being relatively constant, for that particular set of assumptions, here is our graphing of the miss rate versus associativity for different cache sizes, where one way is referring to our direct map cache, and then 8 ways as far as this particular experiment can go. Job of a computer architect is very often to generate these type of figures and to be able to analyze and be able to determine trade-offs in your design space for those particular figures. So higher associativity does mean increasing our complexity. So the question that has to be answered is it worth it? To what extent is increasing our associativity worth it? We looked at the AMD Opteron that made a certain set of decisions in that space. The Core i7 die photograph we saw that made different set of decisions in that same space. And you can start to get the feel for, let's say, an L1 cache here. Our miss rate does decrease, which is a good thing, right? We want as low of a miss rate as possible. Does decrease as our associativity increases, but the answer is ultimately it depends. And the answer is it worth it to increase my associativity? I would look at this chart and I would say, yes, but only for the smaller caches that we have here. That if you have a relatively small cache, in this case for the 1 KB cache, that's a pretty nice linear improvement. Increasing the associativity seems to be worth it. 1 KB of total storage, increasing the associativity, we're reducing our conflict misses, that type of miss in our cache. As we get to the larger and larger caches here, and the points are drawn on top of each other, it's pretty flat. So I would look at, for this case, again, all the caveats apply, for this case, for that data that's generated for a 128 kilobyte cache, a direct map cache seems good enough. Now, we don't know the rest of the equation, right? We don't know how much pain it truly is to go from one way to two way. And there could be fractional improvements here, right? This is a linear graph, and we sometimes want to plot it logarithmically to see, 99 to 99.5 is actually a tremendous improvement in our cache hit rate. So it may still be worthwhile, but it doesn't look like it, at least on this chart. That, yeah, going from 13 down to 9 seems absolutely worth it in terms of a hit rate. But going from 1% to something very close to 1% maybe wouldn't be worth it. At the very least, we could say it levels off, if nothing else. That there's diminishing returns of increasing our associativity for certain sized caches that we have here. For that same exact picture, as opposed to tracing these individual lines, you could actually just look at this as individual column groupings, right? So for a fixed cache associativity, we can look at how we change the size and how that impacts our miss rate. So it's the same exact data as on the previous slide. It's the same exact figure in the text, but you can really draw two different things from it. We know that increasing the cache size is not free, right? We do so, we have to spend the real estate, the transistor budget on the cache to double it in size, and potentially increasing the size also is going to hurt our average memory access time because it's just larger. So larger means it's going to be, take more time to actually access it. But having given all that, we can definitely see that larger is better for our cache by and large, at least to some extent. You see when we look at let's say the two-way set associative bar here, for two-way set associative, seems like 32 kilobytes for this particular application set was good enough. And you're not really gaining all that much by increasing your size, or as we saw here, increasing your associativity. So that's diminishing returns, right? That's flattening of that curve as you continue to increase it. Yeah, I think you could at least say, if your manager came to you and said, I'd really like to explore a 16 megabyte cache for this particular workload, you could come back to this with this graph and say, well, it doesn't seem worth it. We can do it, but are we going to get any real benefits? Because this is only showing the positive aspect of that equation of hit rate. It's not showing what extra pain is associated with having that larger cache size, both complexity, real estate, power, performance, all of those things. We don't really know. We only know the hit rate from this particular analysis that was done here. Let's leave things here for today. If you're bored between now and the end of the semester, continue to read up on this topic of cache architecture and understanding the analysis as practiced in modern microprocessors. I think with that knowledge base, though, you can look at certain announcements that come out in the near future. Like, Apple just released a new version of their ARM chip for their upcoming laptop lines. And they provide enough information that you can actually look at that and understand, well, here's the design decision they made and how that compares to the design decisions that Intel is making or AMD is making, specifically at least in terms of cache architecture. And that's something you can take a look at and have a lot more fluency in now than you would have before the start of the semester at the very least. But that's it otherwise. So everyone please come on Friday. You can also attend this evening that Nolan is having a study session. I don't know exactly what he's covering in that session. I'm planning on stopping by and just listening and seeing his take on things. But that's something that he's having tonight, and we'll have another version of that on Friday. But know that just attending that isn't really counting as being prepared for the exam. I cover my philosophy. I talk about the type of questions that will be on there. You still have to do the prep work. You still have to take the time and be ready for Saturday. I think it's going to go well. I think we're going to be okay. And even if not, the semester's over. So we did okay. We survived to the end of the semester. So otherwise, keep it up. You got really just one more week of academic life this semester. So keep it up and good luck. And I will see everyone on Friday.